Hello friends, welcome to our channel. Here, let's look at the problem for today's daily challenge. Count subarrays where max element of the array appears at least k times. Here, we can solve the problem by two methods. So one is two-point sliding window method. This will be the main focus of this video. And actually, we can also use indexing and counting. This method was previously done in a separate video, but here we are going to quickly go over it after the first method. So first, let's look at the problem statement. So here we are given an integer array called nums and a positive integer k. So we want to return the number of subarrays where the maximum element of nums appears at least k times in that subarray. So if you look at the two examples, so the example 2 is very special because here 4 is the maximum element, but it only appears once in the whole array. Therefore, the output is 0. So if you look at the first example, the maximum element is 3. Its frequency is greater than 2, right? Therefore, the output should be greater than 0. So we need to include at least 2 3s, but the first 3 index. So if you choose to end at either 0, index 1, or index 2, it's impossible to include 2 3s. Therefore, we should examine the remaining indices. So at this second 3, so we need to include the first one, right? So we can start from index 0, and then we can start from index 1, and ending at this 3, right? Therefore, there are 2 possibilities. Well, for the last element 3, so as long as we include the this second to last 3, that will be okay. So the starting index can be 0, 1, 2, 3. There are 4 possibilities. Therefore, 2 plus 4 equals 6. This is the return for example 1. The constraints are the following. First, this nums is not empty, and it can be as long as 10 to the power 5. Therefore, we need to think of time complexity. The elements are strictly positive, and the key is also strictly positive. So with that said, let's look at the two-point sliding window method. So here is the idea for method 1. It's rather straightforward. Basically, for each index, say I use R, right? Find the largest L, which is less than or equal to R, such that nums from L to R is valid. So if this is the case, then you nums from say I to R. So for every I greater than or equal to 0, less than or equal to L would be valid. Therefore, ending at this index R, you are going to have the contribution is L plus 1, right? Then use summation over R, you get the return. So this will be the main idea. It's also the walkthrough we used for example 1. So now let's do the coding. Here I'm going to code the solution using the two-point sliding window with step back by 1. So this is just a specific pattern, right? So first, let's get the length of this nums list. This is for convenience. You can also get the max, right? So now we can initialize a result variable. So we are going to return its final state. This is actually a counting variable, right? And also we want to initialize another counting variable called count, which counts within a window the number of frequencies for m appeared. So now let's initialize the left pointer to be L equals 0. So now we are going to do this for each right index R. We want to find the L. So for R in range n, right? So first I'm going to count. So the count if actually it's checking if the nums are equals equals m or not. You can keep like this, or you can put a parenthesis in order to make it more clear. So let's just write it like this. So in other words, if this nums r equals m, we are going to increment the count by 1, otherwise just increment by 0, right? So here I first do a check. If at this index, so we have count is greater than or equal to k. So what shall we do? We want to find the L such that nums L to R is valid. So this will be the maximum L, right? In the left. This can be done by a while loop, right? While L is less than or equal to R. And this actually we don't need even to write this. We just need to do this. Count is greater than or equal to k. If this is the case, so we're going to shift the L to the right. So we're going to check if this equals m. If this equals m, we're going to decrement by 1. So if originally we have this, so after this while loop, for sure we will have, if L is greater than R, for sure this holds, right? So actually we will have count less than k, right? So in this case, each time we're going to increment by 1. But we want to find this L. But this, after we increment this L, so the current state of L is such that nums from L to 1 up to R is valid. Well, nums from L to R is not valid, right? In other words, L minus 1 is the maximum left index, which makes this valid. Therefore, we need to increment this result by all the possible left starting points for valid subarrays. So this can be 0, 1, 2 up to L minus 1. So there are only in total L operations, because end index will be this minus the beginning plus 1. This is L, right? That's why we increment this L by 1. We should find this L. So therefore, because we want to go to the next iteration, so we need to step back once. So here we are going to step back. So this step back actually is specific to this writing format, but I feel that this writing format is more clear or easy to understand. So actually we need to also go to nums L equals m, right? So this will actually this should be m, right? But let's write in this format. So this way, actually what we do, so for each writing index, we are going to find the largest L to the left such that this is valid. And then we are going to do the count, right? The summation over R. So that the for loop and this update will be summation. So now what we need to do is just to return the result state. This will be the full solution format for using two-point sliding window method. So we can do a test. Yeah, it passes the two cases. Now let's look at the generic case. Yeah, it passes all the cases. So here, in order to better understand this example, let me do some print, right? So for, print f, let's say R, the current state of R. And when we just enter the this round, what's the result? And then after we exit this, so let's say print f result equals when exit. So and then we put another empty line. So now let's look at this. Yeah, for the first example, we know ending and here we have two possibilities. Ending and here we have four possibilities. That is, we have 2 and 4, right? So here are 0, 0, 0, 0, 0, 0. So at index 3, this is corresponding to this 3. So after we exit, so we get 2 valid ones. at this index, after we exit, we get the result to be 6. From 2 to 6, the increment is 4. Therefore, we get 4 different possibilities. So this is for the first example. Well, for the second example, you can imagine, right, because there's no valid ones. So after we exit each index, the result remains 0. So with that print, so I guess we should have a very good understanding for the first solution. So now here, let me quickly mention the method 2. Indexing and counting, right? So actually for this is also very easy to understand, right? So here, let me use this one. So here, let me first, this is the original norms. So let's get the corresponding indices of the maximum element. So actually it appears at the index 1, at the index 3, and at the index 4, right? So here at this index and before the next one, so there's 4, let's call this one, let's call it, let's abstract it. Let's call AI, the index I is 3, right? And the index I plus 1 is 4. Actually, and maybe it can be others, right? 7, but this difference is 1 in very particular. So for all the index starting from 3 and ending before this one, right? That the total count will be I plus 1 minus AI. So here it's just a 1, right? So the right indices. So for this possibilities, then we can look at it because we need to include a 2, right? So here is so we can do what's the left? So left plus 2, left to the current I should have a distance 2. So that is left I minus left plus 1 equals 2, right? So therefore left should be I plus 1 minus the 2. That is the key here, right? So we are going to look at this one, right? So any index up to this and inclusive to this one would be contributed to valid ones. But from 0 to 1 are 2, right? So the contribution at the index this one and ending before 4, the contribution will be this right times so this index. So that is AI plus 1 minus the key plus 1, right? 1 means 0, right? So in this special case, it will be 1 times 1 minus 1 plus 1, that is 2. So get 2, right? And then we look at this index. So from this one up to the end of this array, but here the end is also the 4. There's only one possibility, RS equals, so let's see, let's still use I plus 1. So if I plus 1 is out of bound, you can understand this as the original length of norms. So this is the 1. So the right point. And then we are going to look at this one, right? So any index up to and included to this one can be regarded as the start. So therefore, so the contribution for this one will be RS times again AI plus 1 minus K plus 1. So here it will be 1 times, so here, right, 0 plus 3, not 0 plus 1 plus 3. 1 counts for the 0. So that 1 plus 3 is 4, right? So you add the contribution together, so you get 6. But this way is more efficient than the first way, because for this way we check 1 by 1, but here we check for a range when we compute the right points. So I guess for this it might be same abstract. So you can look at the code here to try to digest, or you can look at our previous video. Now let's first write the solution. I feel that the solution itself is obviously self speaking. So I'm going to use this one as V1. So first I'm going to get the max of this norms list, and then we get the indices, right? So the indices will be I for I, Y in enumerate nums if Y equals M, right? So you can print out this indices. So for this one, we should get 1, 3, 4. But in order for the convenience of computation, so I can do something else. So I can do indices equals the 0, the starting, right, plus the original indices, and plus the length of this nums, right? So you can print it again, right? So what you get 0 and 4, right? 0. So here is 1, 2, 3, 4, 5. Oh, this is the 5. So here I should yeah, 0, 1, 2, 3, 5. So here the length will be 5, right? Minus 4. That's right. So what we do here is that if we want to look at the case one, let's first have it indices. So if we want to look at the second occurrence of this maximum element, we just for this index we just the indices at key, right? Case 2 here, right? So corresponding to the 3. So now let's write the check or the for loop. So first we get a result, and then we're going to do for I in ranges. So we should start from a key, right? And then end at the indices. Actually here -1 because I have increment 2 elements at the 2 ends. So then what we do, first we compute the right possible ends, right? So that will be indices I plus 1 minus indices I, right? So the distance of the number of elements starting from this one and ending at this one will be adding 1, but we don't want to include that one. So this will be the left possible indices will be indices as I computed I plus 1 minus key. But we should count 0, so it should be 1, right? And then what we do is result right side times left side. Then we do return for the result. So then if you let's see, you print that. So here this should be increment, right? Yeah. So it passes. Actually, the same thing, but the second way here, the counting is more efficient. Now let's submit for generic case. Yeah, it passes the case very fast. Notice that here I didn't expand due to the length of the video. You can check the previous video to see how I do the problem before. So here what I want to emphasize is this first version. So personally I feel that if you write like this format, at least for myself, I feel it just translate the idea here into coding format. So I would say we try to write the code such that itself tells you the logic. But sometimes we understand if you look at others' code, so it might need some time to digest. So hopefully this video will help you bring this gap. So with that said, that's it for the current video. So here I want to mention that we have a playlist in our YouTube channel on two-pointer sliding window method. So this method is a very classic but also very powerful one. It can address a quite large set of problems. You should try your best to master it. With that said, that's it. Thank you for watching.